Hello and greetings from Western Australia. My name is Demont Hansen. I'm a senior coastal engineer with the Department of Transport and Maritime. I'd like to thank my co-authors, Darshani Thotogamawage and Lei Tien, who did most of the data analysis, also with Department of Transport and Maritime. And today I'll be talking about an operability investigation of Batavia Coast Marina, which is subjected to gravity, infragravity, and transmitted waves. First, by way of an introduction, the Department of Transport has roughly 50 facilities along the Western Australia coastline from Esperance to Wyndham. A lot of them that are that point towards the west or the southwest, they're subjected to infragravity waves. Two of these specific examples are Batavia Coast Marina, which is what we'll be talking about today, and also Two Rocks Marina. Batavia Coast Marina was built in 1989. Very quickly after that, they realized that it was exposed to wave penetration through northwesterly waves. And so in 2000, we built a northern breakwater extension, which you can see on the right-hand side. This is its present day configuration. Physical setting, as far as bathymetry goes, it's only 40 meters deep up to 10 kilometers offshore. We have a reef edge that gets to about 15 meters, and then we've got a long, wide, shallow reef, anywhere between 2 meters to 6 meters deep. Inside the marina, our water depths are between 5 meters and 2. We've got a shallow sandbar inside of the marina, which we'll discuss more. Wind conditions, summer, we've got a strong sea breeze pattern, which is south and southwesterlies. In the winter, more omnidirectional with some persistent easterlies. As far as wave conditions go, gravity waves, periods between 2 and 25 seconds, significant wave height between 1 meters and 2 meters. We've got dominant direction of the southwest, both in swell and sea. Geraldton is well known for long period waves. It's produced by sea and swell, and its transformation along the long, wide reef flat. Geraldton's well known for long period waves. It's been well researched. There was a symposium, Midwest Ports, in 2014, specifically for long period wave. And you can see Batavia Coast Marina is here relative to Port of Geraldton. The important harbor processes at Batavia, first of all, we have just direct wave penetration of gravity waves, which are diffracted through the entrances and then can be reflected into the marina itself. To some extent, we have gravity wave transmission. Transmission is usually overtopping, but can also be through the structure. Through is a function of stone size, porosity, permeability, and peak period. It's hard to predict, but for long period waves, it can be significant. Quite important at Batavia is our long period infragravity waves. They can be trapped in the nearshore environment. As I said, it's a significant issue at Geraldton. At the Port of Geraldton, when long period wave heights are higher than 0.12 meters, it becomes an issue. Above 0.15, it can be inoperable. But these oscillations in ports and harbors can be predicted by Marion's formula. And I'll show you how that applies to Batavia Coast. So if we look at the longitudinal direction, we predict through Marion's 148 seconds as the fundamental oscillation period, and from longitudinally east to west, we come up with 70 seconds. We can expect in the longitudinal direction, we'll have antinodes at the endpoints with a node in the center. And this is actually a snapshot from some Busenesque modeling that was done in 2014, not associated with Batavia Coast, but they captured the marina in there. So already it's predicting some significant oscillation in long period waves. We can expect at the nodes, we'll have the lowest amplitudes and the highest current velocities. At the antinodes, we'll have the highest long period wave amplitudes and the lowest current velocities. But you can see our jetties A and B are located right near the nodes, so we can expect higher current velocities there. So we do have issues at jetties A and B. Mostly jetty A, we have damages to cleat, so yellow is cleat repairs, red are actual repairs to the fingers. The other bit of evidence and issues that we have a long, shallow sandbar that runs the entire length of the main breakwater. It's considered to be evidence of long period and swell penetration because it's moving sand through the structure. If you dive on it, you can see scour patterns. You see these sort of holes in the voids between the armor, which is very similar to the voids that can develop through significant overtopping and jetting of water through a structure. So this indicates that there can be some wave energy and oscillating current transmission through that structure that can also move sand through. We've had a look at survey data to see if we can see that the structure has subsided in the case that it become much more porous by loss of fines, but we really don't see much difference between the as constructed elevations and the current elevations in 2016. We conducted a roughly 3-year period of wave measurements or Metocean measurements starting in 2014. There were 6 locations, 3 types of instruments. The majority of the measurements occurred between 2016 and 17. I'll go through a few of the instruments. We had AWACs to measure waves and currents, Aquadopps measuring oscillating currents at Jetty B, so right in the center of the harbor. We had pressure sensors at measuring surface elevations, gravity and long period wave measurements set up at 1 second. So they were at all the AWACs, boat ramp, southwest corner, and B jetty. So just real quickly, there's an Australian standard for wave climate in small craft harbors. In general, you're meant to keep wave heights less than 0.15 meters. So when you first look at our inner AWAC location, what we see is that pretty much we always have a good wave climate in 2 years worth of data, and most often also an excellent wave climate. But this is only gravity waves and is not applicable to long period waves. So looking again at gravity waves, this is measurements at the outer AWAC location. This is measurements at the entrance. This is measurements at Jetty B and southwest corner. The upper is significant wave height, and the next panes below are wave height ratios. So what you can see, if you think of it in wave height ratios in terms of transmission coefficients, the entrance in the southwest corner are actually lower than the middle. So if it was diffraction alone, you would expect that transmission coefficients would get smaller as you move deeper and deeper in the harbor. But as you can see, the Jetty B has the highest transmission coefficients of them all. So that indicates to us that there could be some wave transmission through the structure because the transmission doesn't follow diffraction that's expected. But we also interesting to note is that when swell heights on the outer AWAC location are higher, transmission coefficients into the harbor go down. So you can see here where significant wave heights outside go down, then transmission coefficients go up. So smaller swell is more effective at penetrating than larger swell. We also deployed a Waverider that we know as Bob. And we're looking at wave reflection because the assumption is that if wave reflection from the structure is very, very low, that could mean that porosity is high. But when we look at the wave spectrum on the incident wave energy and the reflected wave energy and look at and integrate those spectrum and divide, we get about 30% wave reflection, which is pretty standard for a breakwater. So we don't see any excessive porosity based on reflective measurements. So now looking at long period waves, this is using pressure sensor measurements. This is outside the harbor, and this is at the southwest corner of the harbor. So as you can see, outside the harbor, gravity waves actually are the dominant in the energy spectrum, where if you go inside the harbor, you start to see your 147 seconds and 90 seconds to 70 seconds as predicted by Marians. They become dominant over the gravity wave spectrum. So again, evidence of an oscillating basin. Also looking at long period waves in terms of long period heights outside the harbor versus inside the harbor. So this is swell. Red is swell heights outside the harbor. Blue is long period wave heights outside the harbor. And again, this is inside the harbor. Red is swell. Blue is long period waves. So what you can see that outside the harbor, the gravity waves amplitudes are higher than inside, but then when you get inside the harbor, often long period waves can be dominant over the gravity waves, especially when you reach about a 0.8 meter threshold on significant wave height. Then long period waves can be dominant in amplitude over gravity waves. So it looks like the natural oscillation periods are energized at over 0.8 meters significant outside. Now we're looking at long period waves at different locations. So this is outer, just significant wave height and long period wave height. And these are ratios of long period wave heights outer versus at the various locations. So what you can see, wave height ratios are much higher at the antinodes, both the entrance in the southwest corner and are lowest at the nodes in the center. And again, just more evidence that it's an oscillating basin in its fundamental mode. When we look at oscillating currents measured by the Aquadopp, what we see, we're looking at longitudinal oscillating currents, so north to south, or transverse currents, east to west. You can see the oscillating currents associated with long period waves are more energetic than gravity waves, north to south. But then when you look east to west, you have a bit more energy actually from gravity waves. So this again can indicate that there is some transmission through the structure, allowing gravity waves in. So just in summary, we've got a well-known energetic long period wave climate in Geraldton. At certain wave heights and natural oscillation periods of the Batavia Coast Marina are energized. Most of the wave energy or the harbor energy is in the long period wave bands. There is some moderate swell energy by penetration, and there is some evidence of transmission through the breakwater, which we need to investigate further. And effectively, oscillating currents are superimposed on gravity, on infragravity, so it means that you can effectively have resonance every 10 waves, which can end up moving the boats quite a bit. Anyway, thank you very much for joining me today, and I hope you have a really good rest of your conference. Thank you very much.